This is my fourth lab for Physics 2. So the purpose of this lab is to use the energy conservation, the loop rule, and the current conservation, node rule, to make predictions about current and voltage within circuits. And we want to compare these predictions with the actual values in a circuit using ammeters and voltmeters. This is experiment 1. We also want to examine the behavior of ohmic resistors and capacitors in an RC circuit in experiment 2. So the fundamental concepts include the node rule, which is the conservation of energy, which details that the potential difference in going around the loop of a circuit must be 0. The node rule, which is the conservation of current, which is that the net current flowing into a node and out of it must be equal. Ohm's law, which is voltage is equal to current times resistance of a ohmic resistor, and the formulas for capacitance and the time dependence of voltage across a resistor in an RC circuit should be that of exponential decay. So the model that I'm going to be using is an online circuit construction kit that simulates real-life circuits and circuit rules. And so we would assume that it has the same function as a real-life circuit. And thus there is negligible resistance of wires, negligible resistance of ammeter, and all the EMF of the battery should go towards the resistors, which are ohmic. So a preview of the results is that in the first experiment, the predictions line up with the observed values. And in experiment 2, the graph of measured time against voltage was that of exponential decay. So in the first experiment, our setup, we want to connect two 1.5 volt batteries to create a battery of 3 volts to a 47 ohm resistor, a 100 ohm resistor, and 2 ammeters all connected in series. Using our node rule and loop rule calculations, we should find that the current measured in the ammeters should be 0.02 amps. Upon doing the experiment, we see that the ammeter readings both show a current of 0.02 amps, and replacing one ammeter with a voltmeter gives 0 amps current but a 3 volt potential, which means that there is no current, so the circuit is closed. In other words, the voltmeter has an infinite resistance, but there is still a potential difference equal to the EMF. We then take out one of the ammeters and using a voltmeter measure the potential difference across the different parts. Our predictions are that across the two batteries it should give us the EMF, which is 3 volts. Across the 47 ohm resistor it should be negative 0.96 volts since it uses up some of that EMF. And across the 100 ohm resistor it should be negative 2.04 volts, while the rest of the components have 0 volts because they have 0 resistance. The results show, which you can pause the video and take a look, that it does actually agree with the predictions made about the experiment, just that the voltage values are flipped because I flipped the terminals during this experiment. Here you can see the graph. At the first red section is when the voltage is increased by the battery, and the blue sections show the voltage being used up by each of the resistors. If we connected the ammeter in parallel to one of the resistors, what we see is actually an increase in the current. This is because the ammeter has a very, very small resistance. So connecting it in parallel decreases the effective resistance of the ammeter loop. And thus, since there's less resistance but the same EMF, the overall current increases. Using the measured values, we can thus calculate the resistance of each of these resistors, for which we get 48 ohms and 102 ohms, while for the wire and ammeter we get 0 ohms. The difference between the actual values and the calculated values are due to rounding error, since the ammeter and voltmeter are only precise to 2 decimal places. Moving on to the second experiment on the RC circuit, we want to connect a 9 volt battery to a 10 ohm bulb and 200 millifarad capacitor in series. And we see that the bulb grows brightly and fades away as the capacitor charges, but then when we discharge it, the same thing happens because the current is decaying exponentially from a maximum to 0. When we replace the bulb with a 20 ohm bulb, the fade away was longer. It took 14 seconds to charge and 16 seconds to discharge than for the 10 ohm bulb. To perform the quantitative experiment, we want to set up the same circuit, except this time with a 30 ohm bulb in series, and connect a voltmeter in parallel to the capacitor. We're going to charge the capacitor it is fully charged, and then remove the battery and discharge it. Then we want to use a stopwatch to measure about 20 seconds worth of the capacitor discharging, and then plot a linearized graph against time to find the slope. Upon performing this experiment, we do see that the voltage versus time graph is that of exponential decay, and the linearized graph gives us a slope of negative 0.1672, which is very, very close to the expected value of negative 0.1667, and thus we can conclude that this experiment does in fact prove the time dependence of an RC circuit. Since this circuit was online, it was an idealized simulation, so external error or human errors were minimal, so the only sources of error would have been computational, such as rounding errors due to the precision of the measurement apparatus. So some questions. So what if I was doing this lab in real life and use an actual ammeter? Then a real ammeter would have a very small but still non-zero resistance, so it would lower the overall current in the circuit, but it would be small enough that it would be negligible for the scope of this experiment. Furthermore, if I used a real battery with no resistor in the circuit, it would charge very quickly since the resistance of the wires is close to zero, but it's still non-zero. The slope 1 over RC would approach infinity, leading to an almost instantaneous charging or discharging of the capacitor.